This video, we're going to focus on finding vertical and horizontal asymptotes. And our goal is to start graphing these rational functions by hand, getting some good sketches. So let's start with vertical asymptotes. You might remember with the toolkit function, 1 over x, that when we graphed that, it has a vertical asymptote at x equals 0. Now, we know that x equals 0 is a problem if I try to plug it into the actual original equation, because I get 0 in the denominator. And that's the key for vertical asymptotes. We need to find where the denominator equals 0. So that's what I'm going to do. I'm going to take that denominator, set it equal to 0. Now, it is in descending order, and I could factor it as it is, but most students are more comfortable when it's in the right order from what they've seen. So I'm going to go ahead and put the x squared first, which is a negative, and I'm going to also multiply everything by -1 on both sides. So I could either factor out a -1 on just the left side or multiply by -1, which basically gets rid of the negative. Okay, and now I'm going to factor this. So this factors into x plus 2, x minus 1. Since 2 times -1 is -2, but 2 plus -1 is +1. Setting those two pieces equal to 0, I get x equals -2 and x equals 1. And there are my vertical asymptotes. So the process is to set the denominator equal to 0. And let's look at another example. So for this one, if we set the denominator equal to 0, and as you could see, they asked us to use technology, so there's probably something interesting that's going to happen here. Now, I could just add 4 and take the square root, but because we just did some factoring, I'm going to factor, and also because I know what's coming. If I factor it as to x minus 2, x plus 2, then I get x equals 2 and x equals -2. Okay, so we want to graph this. Let me go ahead and pop over into Desmos and attach my keyboard. So we are graphing. I think they called it k of x equals, I'm going to put it in parentheses, x minus 2 divided by, so now I put the whole thing in the numerator, x squared minus 4. All right, and let me go ahead and zoom out. This was zoomed in from another picture. Okay, so that looks very similar to the 1 over x reciprocal function, the toolkit function, but I noticed that there's only one vertical asymptote. I'm missing the vertical asymptote at 2. So here, I'm going to kind of select 2. And sorry, it's not even letting me select 2. So here's what I'm going to do. I'm going to cheat. I'm going to come over here and I'm going to say, haha, what happens at 2? And notice at -2, it's undefined, but it's also undefined at 2. Okay, so what happened? It says it's undefined, but there's no vertical asymptote there. So let me go back. Here's what happened. And you might have noticed it. The original function, k of x, is x minus 2 over x minus 2, x plus 2. And here's what we see. X minus 2 actually cancels. So really, this equation, or equation for k of x is equivalent to 1 over x plus 2. Now, the x minus 2 doesn't actually go away because the x minus 2 does in fact limit our domain. So it's still part of the domain, which means we're saying that x can't be positive or -2, period. It can be anything but positive or -2. But as far as vertical asymptotes go, we only have one vertical asymptote, and that's at x equals -2. So when we're able to reduce a rational function, what that does is actually create a hole in the graph. And that's what that says right here, vertical asymptotes and holes. Sorry, got mad at me because I selected it, and of course it's going to do the keyboard. All right, leave me alone. So at points where both the numerator and denominator of a rational function equals 0, factor the numerator and denominator and simplify. The simplified function will have a vertical asymptote, and they will have a hole at that point. Now, because Desmos is a computer, it's kind of stupid, and it doesn't quite know how to draw holes in the function. But what that means is, wow, it's very small. What that means is if I were to actually graph this function, here's the vertical asymptote that showed up. And then at x equals 2, it's going to literally have a little hole in the function. So it's going to keep going. It's going to have a hole right there and then continue on its merry little way. So there's literally a hole at that point. Now that comes into play in calculus. Working with functions that have holes is actually something that is part of the calculus sequence. So this information, though we're not going to really worry too much about the graphs of it, it is something that you're going to see later on if you continue into calculus. Okay, so let's come back down here then. And let's talk about horizontal asymptotes. Now, horizontal asymptotes are a lot more complicated than vertical asymptotes. There are actually 3 cases for horizontal asymptotes, and we determine these cases by the degree of the numerator's polynomial versus the degree of the denominator's polynomial. So in the numerator here in this first example, this is degree 1. And the reason it's degree 1 is the highest exponent on the variable is 1. In the denominator, this is degree 2 because the highest variable exponent is 2. So we have case 1, which is the degree of the denominator is bigger than the degree of the numerator. So here's what happens in this case. In this case, the horizontal asymptote is automatically y equals 0, period. Now, there's a reason for this, and I don't really want to get into the giant explanation, but a basic reason is they basically take the first 2 leading terms of the polynomials and kind of look at them and compare. And they're like, okay, so if I'm looking at those, I have 3x over x squared, which, by the way, an x cancels in the numerator and denominator, and I'm left with 3 over x. Well, that's a vertically stretched version of the reciprocal function, and it has a horizontal asymptote at y equals 0. So there you go, y equals 0. Now, that's just kind of a general explanation. So this is basically the reciprocal function, and it has a horizontal asymptote at y equals 0. All right, now why we do this comparison, they're not going to really explain. That's kind of something you get into more detail with in calculus, but there you go. That's how we generally look at it. Okay, so let's look at the case where the degree of the denominator is smaller than the degree of the numerator. So the numerator is bigger. Okay, so in this case, if I kind of do the same game where I take, oh, sorry, let me just really quickly comment. So the degree of the numerator in this case is 2, and the degree of the denominator in this case is 1, so it's reversed. Okay, so if I kind of play the same game where I take the leading terms of the 2 polynomials and reduce them, I get 3x. And 3x has no horizontal asymptote at all. 3x is just a line. So in the case where the degree of the denominator is smaller than the degree of the numerator, there is no horizontal asymptote. Actually, there is a different type of asymptote called a slant asymptote or oblique asymptote. So it's an asymptote that's actually slanted like a line, which kind of makes sense because we got a line here, 3x, I said that's a line. But there is no horizontal asymptote in this case. So when the degree of the denominator is smaller than the degree of the numerator, no horizontal asymptote. Okay, The last case is when they're in fact equal. If they're equal, using our comparison, so in this case, numerator has a degree of 2, denominator has a degree of 2 also, comparing the two front terms, or yeah, two leading terms. That simplifies to 3. And oops, sorry, my screen moved while I was trying to write and it gets mad at me when that happens. That is the horizontal asymptote. So the horizontal asymptote is y equals 3. So the horizontal asymptote, and here I'm going to abbreviate that, HA, the horizontal asymptote is the ratio of the leading terms. So if that had reduced to a 5, it would have been y equals 5. If it had reduced to a -1, it had been y equals -1. Okay, you get the idea. And this sums up what we just said. Horizontal asymptote is 0. No horizontal asymptote. Horizontal asymptote is a ratio of the leading coefficients. Cool. All right, so let's look at an example we saw earlier, the sugar concentration example. In this example, we created an equation, and they are asking us to find the horizontal asymptote in this example and then kind of make sense of what it means. All right. So I'm going to look at the degree of the numerator and denominator. So degree of the numerator in this case is 1 because t is the variable and it is a degree of 1. Doesn't look like a D, does it? Looks like a sad A. Okay, let me fix it. There we go. Degree of the denominator is also 1. Okay, so this is the case where it's going to be the ratio. I am going to be basically using these two terms, those high exponent terms, even though they're not technically in front. I could have rearranged the equation so that they were. I could have put -t plus 5 over 10t plus 100. Oh, I'm sorry, that's not a negative, that's a positive. My line just went right through it. No negative. All right, I could have rearranged it and then done the leading coefficients or terms. Okay, so let's reduce it. T over 10t reduces to 1/10. And there is our horizontal asymptote, y equals 1/10. Now, what this means, though, is that as we are putting in, or I'm sorry, as t is increasing, we're basically seeing like kind of a concentration of sugar that never really exceeds 1/10. And this was, I believe, 1/10 per pound. I'm sorry, 1/10 of a pound per gallon. So if we were to kind of explain this, we're saying that the concentration after a lot of time reaches kind of like an equilibrium. I'll call it that, an equilibrium concentration of 1/10 pounds per gallon of sugar to water. 1/10 pounds of sugar per gallon of water. All right, let's look at another example. Find horizontal and vertical asymptotes. Okay, now this one's already factored, which is so nice. Let me take a second, make sure none of the factors are going to cancel, which would mean we would have a hole in the graph. None of them do. Okay, so we can just go ahead and for the vertical asymptotes, we're going to set the denominator equal to 0. So I'm going to abbreviate denominator DEN equal to 0. So that means x minus 1, x plus 2, x minus 5, all equal to 0 is going to give me x equals 1, x equals -2, and x equals 5. So we have 3 vertical asymptotes. All right. Now, horizontal asymptotes, we have to look at the degree of the numerator versus the degree of the denominator. So if I were to start multiplying this out, if I were to FOIL or distribute, in the numerator, I'm going to end up with degree 2, right? I'll get x squared. But in the denominator, because I'm going to multiply 3 of them, I'll end up with degree 3. So this is a case where the degree of the denominator is larger than the degree of the numerator. And in that case, then the horizontal asymptote is automatically y equals 0. Okay, so now we're going to move into finding intercepts. And for intercepts on these graphs, we end up kind of focusing on the pieces we've been slightly ignoring. So vertical intercept is found when we actually plug in 0. So we find the vertical intercept by taking f of 0 and figuring out what value that equals. I'll just call it number symbol for some random number, okay? Horizontal intercepts is what happens when the whole thing equals 0. Now, if we're working with a rational equation, meaning we have a fraction equals 0. Oops. A fraction equals 0 when the numerator is 0. Which really means to find the horizontal intercepts, I need to set the numerator equal to 0. So let's look at that in the example we just did. Let's find the intercept. So we're going to find both the x-intercept and the y-intercept, or in this case, they've been calling it vertical intercept versus horizontal intercept. So the vertical intercept means I'm going to plug in 0. So that's going to give me 0 minus 2, which is negative 2, times 0 plus 3, which is 3, which is going to be negative 6. In the denominator, 0 minus 1 is negative 1. That's going to be times 2, which is negative 2, times negative 5, which is positive 10. So this is going to be negative 3/5. So the vertical intercept is at 0, negative 3/5. Okay, horizontal intercept, I'm going to abbreviate it. That's going to occur when we set the whole function equal to 0, but really I'm setting the numerator equal to 0. Oops, I meant to put an M. Num equal to 0. So x minus 2 times x plus 3 equal to 0, which they were so nice and factored for us. So this is going to be x equals, positive 2, negative, and x equals negative 3. So these are 2, 0, and negative 3, 0. There are our horizontal intercepts. Nifty. All right. So they kind of sum up graphical behavior when we see these rational functions to kind of help us with graphing this whole thing. So if a rational function contains a factor of the form x minus h to the p, meaning it has a power, the power helps us kind of figure out what type of pictures we have. If it's a power of 1, we see this kind of behavior around the vertical asymptotes where it goes opposite directions. And maybe it goes opposite directions if there's a negative coefficient. But if it's an even power, it kind of behaves like the squared reciprocal function does, the x squared, 1 over x squared, and they both go the same direction at the vertical asymptote. So when we have vertical asymptotes that might have a square on it, what that means is the graph is going to have both sides approaching the same value. Okay, so let's kind of see this in practice. They ask us to sketch this. And we are going to rough sketch it, but we are going to find some important pieces of information to help us do it. First thing I want to note is the vertical asymptotes. Oops, horizontal asymptotes. Wow, it is just, there we go. Vertical asymptotes, horizontal asymptotes, or asymptotes, sorry. And then the x-intercepts, which is the horizontal intercepts, and the y-intercepts, which is the vertical intercepts. So I want to find all that information, and then I'm going to use that to help me graph. Okay, vertical asymptotes, I'm taking the denominator, setting it equal to 0. I'm seeing an example of a squared, which is going to have both sides approaching the same way on that particular denominator. I'm sorry, that particular vertical asymptote. So if I set this equal to 0, I get x equals -1 and x equals 2. So there's my two vertical asymptotes. And at -1, they're going to be going the same direction. Okay, horizontal asymptotes. So let's see. We got to figure out the degree of the denominator versus the numerator. So the degree of the numerator, actually here, I'm going to do it up here by the degree up here. So if I multiplied that out, I'm going to end up getting x squared. But if I multiply this out, I end up getting x cubed. I have 3 x's there. So degree of the denominator is bigger, y equals 0. Nice. That makes our life a little bit easy. Okay, x-intercept, setting the numerator equal to 0 this time. And they were so nice to factor this for us. So this one, we're getting x equals -2 and x equals 3. Great. So those are the points -2, 0, and 3, 0. And then last, the y-intercept. I'm going to plug 0 in for this. Okay, and here I'm going to kind of work it out a little bit in my head. So I'm going to get 2 times -3, which is -6, over 1 squared, which is 1 times -2 is -0. So that's 1 times -2. Oh, so yeah, it's a +2. Interesting. That's interesting because I saw the graph and I thought it was a fraction. That's why I'm pausing here. So let's see. Plugging in 0, 0 squared is 1. Yeah, it's a -2. All right, I'm getting 3. Fine. All right, so maybe I looked at the wrong graph. Fine. So this is what I'm getting. And maybe this is wrong, so I'm a little skeptical on the y-intercept. And it's the last thing we're going to graph, so we'll deal with that. Okay, here we go. So we're going to rough sketch this. So x equals 2, we'll have the first vertical asymptote. X equals -1, we'll have the second. And then we also have 3, 0 is a magic point, -2, 0 is another magic point, and then 0, 3 is apparently another magic point. Okay, so here, just gonna fill out these tick marks. Okay, vertical asymptote at 2. I'm gonna go ahead and put a dashed line at 2. Vertical asymptote at -1. Horizontal asymptote at 0, which is right along the x-axis. And then the graph crosses at -2, 0, which is right here. It crosses at 3, 0, which is right here, and supposedly right there for the vertical intercept. All right. Oh, I just realized now I know why I was having trouble with it. I was looking at the wrong graph when I did this. Okay, yay, I feel better. All right. So here we go. Let's look at this graph. So at x equals -1, I'm sorry, let's start with x equals 2. Okay. At x equals 2 as our vertical asymptote, I know my graph is actually crossing the horizontal asymptote. I'm just now realizing this. That's interesting, isn't it? We don't see this very often where it actually crosses the horizontal asymptote, but it is possible. What happens in those cases is our graph kind of approaches those values. All right, so let me plug in like 4 really quick. I want to see what's happening when x equals 4. So if I plug in x equals 4, I'm going to do this in blue. If I plug in 4 for x, here, let me do it over here. F of 4. All right, I'm going to get 6 times 1 over 4 is 5 squared. That's 25 times 2 is 50. Okay, so I'm getting a really small positive fraction. So that means that over here it's above. So it's implying that this is doing this. But because there's a horizontal asymptote, this thing is going to start approaching the horizontal asymptote as it keeps going. So it kind of jumps above it for a second, and then it's going to start rapidly approaching as it keeps going on forever and ever. Okay, now because this vertical asymptote at x equals 2 is odd, that means the other side starts up. And then it goes here. All right. And then we need to figure out if it's going to kind of shoot downwards or upwards. So we need to plug in another number here. Oops. Let's plug in 1/2, negative 1/2. And again, I'm just trying to figure out if I have a positive or negative here. Negative 1/2. Okay, so negative 1/2 is going to give me a positive number in the numerator times a negative number, which is going to be a negative in the numerator, over a positive number here times a negative number. So it ends up being a positive value. I'm not really figuring it out. And if you grab your calculator and calculate it, that's fine. But what that means, though, is that this thing is actually going to loop back up here and approach above from the left. So then that means that this graph is going to cross right here and kind of do the same thing as the other side. It's going to then start approaching the horizontal axis. Wowzers, that was a complicated graph. But I wanted to show you a pretty complicated example so that way you could see some kind of interesting cases. Of course, when you're doing the homework, you can use Desmos to guide you, but on an exam, you want to kind of be able to do these sketches with the information you're given quickly. All right. For this one, they want us to write an equation for this, and therefore we'll kind of pick out the pieces we need. So first thing I notice, I'm going to start with vertical asymptotes. I see that I have a vertical asymptote at x equals 2. Because it goes the same direction, it's squared. It's a multiplicity of 2. I have another vertical asymptote at x equals -1. That one has them going opposite directions. So that's just a multiplicity of 1. So in the denominator, I have an x minus 2 squared and an x plus 1. Cool. Okay. Similar to what we just saw. See how it's like crossing here, but it looks like it's approaching y equals 0 on both sides. That implies to me that the degree of the numerator is smaller than the degree of the denominator. And right now the degree of the denominator is 3. I'm seeing that that's a horizontal asymptote at y equals 0. So that means that these two x-intercepts, x equals -2 and x equals 3, are going to make up the factors in the numerator. So in the numerator, then, I have an x plus 2 and an x minus 3, and no squareds, because that is degree 2, and that's smaller than the denominator. Nice. So the last piece is to see if maybe there's some sort of coefficient out here in the front. And I'll call it A for right now. And I need to see what A is, and I'm going to use the last piece of information, the y-intercept. So the y-intercept happens at 0, -2. So when I plug in 0, I get A times 0 plus 2. I'll write it out since we're showing this work. 0 minus 2 squared, 0 plus 1. Okay, so let's see. That's going to be -2. That's what that ends up equaling. And over here, I have A times -6 over, that's 4 times 1, so 4. So I'm going to multiply the 4 onto the other side. Oops. It's so mad when I move it and it's not ready for it. Going to do it again. Okay, multiply the 4 to the other side. Boop, boop. And I'm left with -8 equals, let's just do -6a. We'll write it like that. Okay, so A comes out to 4/3. So our original, or our final rational function, let me go ahead and actually give myself a little more space. There we go. Is f of x equals, okay, so 4/3, I'm going to put a 4 in the numerator, 3 in the denominator, and then x plus 2, x minus 3, x minus 2 squared, x plus 1. And then we can verify that on Desmos that it does in fact give us this graph.